I mean, yeah, the average on that first test was the lowest I've ever seen in the 28 years I've taught this class.
Don't say that.
I know.
Don't say that.
Makes me feel a little bit better.
Oh!
Oh,
Welcome back!
Hi.
oh.
What's happening?
Insomnia.
Insomnia?
Yeah.
Well, you should be wide awake then.
I am. I am.
Wide awake? Let's see. All right, well, let's. I don't think, yeah, these are all the folks that seem to be wanting to return. All right, well, so we're in the process of integrating powers of trig functions, powers and products, products of powers, all that stuff. And we're dealing with tangents and secants. And there's two rules, a little more complicated than the sine and cosine rules. The sine and cosine rules, if one of them has an odd power, pull off one factor and convert any that you left behind. So with tangent and secant, we did two examples. And the two rules were if secant was to an even power, we wanted to pull off a pair of secants. So pull off a secant squared. Why would we do that? So if we pull off a secant squared and we put it over with the dx, what is our plan to let u equal?
Squared.
If we put secant squared with the differential, so let's go ahead and just start this one. So we want to be thinking about what our plan is. So here I know that one of the rules says if secant is to an even power, we're going to pull off a pair and stick it with the differential. So let's suppose we've done that. We see that it's square, but what is our plan? What would we want to let u equal if we put secant squared in that box?
Secant.
Nope.
Tangent.
Tangent, right? Because the derivative of tangent is secant squared. So if we have everything in front here all tangents, if we let u be tangent, its derivative is now over here. So if we pull off a secant squared, our goal is to convert anything to the left of that, make sure it's all tangents, so that if we let u be tangent, then we can replace the secant squared d theta with a du. All right, so we pull off secant squared, and we want to turn everything else to tangent. So these things right here are what I'm referring to as the leftovers. So these are leftover. We took the secants, we pulled two off, we left some behind. Now we want to convert those over to tangents. And so we need to have our identity dialed. This is the identity rectangle. Oh my gosh. The identity triangle. This reminds me of I just heard the craziest thing by some national politician yesterday. He was talking about chopping the budget for the Pentagon. He's like, we need to turn the Pentagon into a trigon. I'm like, do you mean a triangle? A trigon? It's like, go back to Alabama. A trigon. It's like, what is that? Oh my God. So, you don't have to be educated to be a politician. This is the moral of the story, I guess. Oh my gosh, I just laughed so hard. I never heard anyone, even a kindergartner, refer to a three-sided polygon as a trigon. So we need to convert these leftovers with this triangle. There's our identity right there. Tan squared plus 1 is secant squared, so secant squared is tan squared plus 1. So we're just going to use that. So tangent squared plus 1. And now we're in a position that substitution is going to work really beautifully. All Right? If we let u be tangent here, then all the stuff in front of secant squared d theta becomes polynomial. So that's going to be our substitution. We're going to let we're going to use a u to be tangent. So then du is going to be secant squared of theta d theta. My mom lived in Alabama for 35 years, so I'm allowed to bash Alabama. I can make fun of Alabama. So this becomes that. And so this integrand, with all these polynomial, with all of these trig product things, this is kind of what our goal is. Our goal is, can we somehow turn it into a simple polynomial integration? That is kind of our strategy. And most of the time we can. Oh, I should be going full screen. So then our last step is just to back substitute. We just need to go back. We said u is going to be tangent, so we're going to go back. And there we go. So there is our family of antiderivatives, the indefinite integral, our final answer, all that stuff. Any questions on any of the pieces you see there? So the rule we used said if secant was even, pull off two secants and convert any remaining secants, any secants you left behind. Now the other rule actually could be used here as well. So remember that the other rule says if tangent is to an odd power, you can pull off a sectan. So if we pulled off a sectan, so if tangent is to an odd power, we could pull off a sectan. And what would we be wanting to let u equal if we pulled off a sectan? Secant. Because then sectan d theta, or whatever the independent variable is, will equal the derivative of the u. So you could do that here because tangent is odd, the power is odd. But if the power on tangent's odd and you pull off a tangent, then the power on tangent becomes even. We would have a tangent to the eighth. So if we went the other way here, that would be a lot more work. We have two choices. We could convert secant squared, or we could convert tangent to the eighth. So I chose to convert secant squared. Converting secant squared is a lot easier than tangent to the eighth. If we were going to convert tangent to the eighth, we know that tan squared is secant squared minus 1, but then that would have to be raised to the not the eighth power, because tan squared, it would have to be raised to the fourth power. So then we would have to do a superfoil, all raised to the fourth power. So replacing the secant squared is a little more logical. All right, let's take a look at this one. So our rule is that if secant is to an even power, pull off a pair, or if tangent is to an odd power, pull off a sectan. This is not an even power in our estimation here. When we use this rule, we mean, so first off, if we were to rewrite this so that we had positive exponents, yes, the power on secant is even, but what we really mean is that the power on secant is even in the numerator, so that you can pull it off and put it with the dx or d theta. So this is not going to count. We can't use the secant squared rule here. There's no secant squared in the numerator that we can pull over. So we definitely are going to use our tangent rule here. And so the rule for tangent says, if tangent is to an odd power, we want to pull off a secant times tangent. But again, we don't see a secant in the numerator to pull it off with the tangent. So we use our magic bullet. We multiply by 1. So we're going to multiply numerator and denominator by 1. And the form of 1 that we are multiplying by will be such that we now have a secant that we can pull off. So we're going to pull off our sectan. And when we pull off our sectan, here's what's going to be left over. So we're pulling off a sectan. Secant theta, tangent theta. That's going to hang out with the differential. It's going to go into this little box over here. Our blue box. All right. And so the function that has sectan as its derivative is secant. So our goal is that we want to have just secants over here. So if we let u be secant, that'll turn all the stuff right here into polynomial expressions. And then the derivative of secant is sectan, so that will take care of the differential. All right, so we need just secants. So our focus was on tangent. We had an odd power of tangent, so we pulled off a tangent with a secant, and that's always going to leave an even power behind on the tangent, which allows us to do the conversion. The conversion is always through a Pythagorean theorem, so we have to have an even power there. So we are going to be left with tangent squared. If we look at our identity here, tan squared is secant squared minus 1. Tan squared is secant squared less 1 divided by secant cubed times sectan. So there we go. Now we're ready for our substitution. So we're going to say u is equal to secant, which makes du equal to sectan. And now we're rolling. This will be u squared minus 1 divided by u cubed, and then times du. So everything has been turned into polynomial expressions. Now we're going to split the fraction. So we're going to divide the u cubed into each part of the numerator. So we'll have a 1 over u. And then here we'll have a u to the minus 3. So I'll write it like that. It's easier to integrate for most of us if we have a negative exponent. The integral of 1/n is natural log absolute u. And then integral of u to the minus 3, we add a 1 and divide by the new exponent. So we're going to add 1 to that and get u to the negative 2. And then dividing by negative 2 is going to make this plus 1/2 out in front. And then we have our integration constant. Final step, back substitution. Natural log of absolute value of secant of theta plus, that will be 1 over 2. U is secant, so we're going to have a secant squared in the denominator plus c. What if we don't like having a trig function in that denominator? How could we rewrite that so that we don't have a trig function in the denominator?
Use a negative exponent.
You could use a negative x
Cosine.
cosine, right? A secant down below is equivalent to a cosine up above. So we could just write that as cosine squared. Plus c. All right, any piece of that you want to pick apart? Not sure about? So our big rule of thumb is that whatever we're pulling off, that needs to be the derivative of whatever we're going to let u equal. Yep.
Is it necessary to bring the secant to the denominator, or can it just be tangent squared times secant to the -3?
Let's see, where are we at? Over here?
Yeah, just anywhere from the beginning.
Yeah, you can do
You
that.
could just leave the negative.
Absolutely,
Okay.
absolutely. Usually with trig functions, it sort of feels weird. We have to be careful. One of the reasons we always tend to write positive exponents on the trig functions is that we want to be really careful of this type of thing, right? Because this is not 1 over secant, 1 over sine. Right? That's the inverse function. So if you were to write secant to the -3, because it's more than just -1, you might be able to get away with writing it like that, but really the way you should be writing this, as soon as you have a negative on a trig function, you really should be writing it like that. Because we don't want to confuse, we use this notation to represent the inverse, not the reciprocal. So we just have to be careful if we're going to use a negative exponent on a trig function. That's not the inverse. Just got to be aware of that. All right. Yeah, let's see. I think those. All right. So let's take a look at this. These are sort of generalized reduction formulas. You do not need to know them. The only two reduction formulas we need to know in here are for sine squared and cosine squared. Those are the only two you need to sort of memorize. But there's all these formulas, just in case you have powers on trig functions, that these formulas are generated with integration by parts. There's all sorts of complexities in doing it, but you don't have to memorize it. If I ever asked you to do something that had this type of power, so a power on secant that's odd, we already know how to do it if it was even, pull 2 off and convert the leftovers. But if the power on secant were odd, like this, you'd really have to go to here unless you wanted to do a very difficult integration by parts multiple times. So I'm just going to do one here, make sure you sort of get the idea. So if we are looking at this last formula here, secant to the n, we're thinking of n as 5. And we just sort of do what it says to do. So we subtract 2 from the 5, and we get secant cubed of x. So wherever there's an n, all we're going to do is come in and plug in the 5. So we're going to have 3 over 4 integral secant to the 3 of x dx. So we have that. And then we're in the same boat again. This reduction formula has dropped the power on the function that we're integrating from 5 to 3, so we're going in the right direction. Now n is 3, and we're going to do the same thing. So we're not really doing math. We're just sort of, understanding how this formula works, this integration table. But important to be able to do. It's not something that we really test you on. It seems pretty intuitive. So now n is 3. We're going to do the same thing. So we're going to take this integral, replace all the n's with a 3. So we have 3 minus 2, so it's going to be sec tangent. There's going to be a big bracket out in front. So So sectangent, and then 3 minus 1 is 2, so divided by 2. And then we're going to add 3 minus 2, so 1 over 2. Integral. Now secant's going to have a power of 1. And so we end up with that. So let's do a little distribution, and let's talk about that integral of secant. And let's remember a fact that we talked about last week. So plus 3/8 here. So integral of secant. We said last week that, we at least noticed that other than sine and cosine, so the other 4 trig functions, tangent, cotangent, secant, cosecant, they all integrate to log functions. And so we also said that any trig function that integrates to a log function, you should be able to use your magic bullet, multiplying by 1, to put it in what we've called in this class log form. Log form being an integrand where the denominator's derivative is the numerator. And so what we're going to do for this, to put it in log form, let's put a little space here, and we'll put our dx there. Does anyone remember the form of 1 that we multiplied top and bottom for here for this situation? So the hint that I, or the way that I, say again?
Tangent.
Not just tangent. If you multiplied by tangent, let's just suppose we multiplied by tangent, then the numerator would become sectan, and the denominator is tan, but the derivative of tan is not sectan, so it's not quite there yet. So the suggestion I had was I asked you, what is the derivative of secant? Sectan. And so then that just gives us a clue as to what this multiplication is. That's how I remember it. Derivative of secant is sectan, and what happens is if you multiply top and bottom by sec plus tan, you get it. So let me rewrite this so we can see that that I'm telling the truth. So in the numerator we would have secant squared of x plus sectan. And in the denominator, we have sec plus tan. So let's see, I already distributed. I don't need that bracket anymore. Is that in log form? What is the derivative of secant? Sectan, right there. There's its derivative. What is the derivative of tangent?
Secant squared.
Yeah, secant squared. So now it's in log form. So this is the tricky one that you will see it quite a bit this semester, and you probably will end up memorizing what the antiderivative is. But that's how we get it. We get it by multiplying by 1 in the form of secant plus tangent, up and down. So this is going to be 3/8 natural log absolute sec plus tan. All right, so that's how those more generalized reduction formulas work. I'm just going to, it's kind of like cooking. Just follow the recipe. N is 5, plug it in. N is 3, plug it in. Any questions on any of the steps? Okay, let's do a quick review again. We've talked about this a few times now, but all 4 trig functions other than sine and cosine can all be put in log form. And we looked at this with the hyperbolics also, because the same thing is true. And so here, with tangent, we replace tan with its quotient, sine over cosine. And then we ask ourselves, is that in log form right now? And it's not in log form yet, right? Because the derivative of cosine is negative sine. So we use our magic bullet. We force the numerator to be what we want it to be. But then we have to remember to balance that out. So we put a minus on the outside. So we haven't changed the value. We've just changed the look. Now it's in log form. And once it's in log form, we get minus natural log, absolute value, denominator plus c. So we get that. And if we wanted to be, clever here, we could say, ooh, there's a minus 1 in front. And we know that coefficients of logs, their magic power is that they can fly up into the inside and become an exponent. So you could, if you wanted to, take that and fly it up here, and then you would be asking for the reciprocal, not inverse, but the reciprocal of cosine. And what is the reciprocal of cosine?
Secant.
Secant. So you could, if you wanted to, write it that way. So either of those is totally fine. Certainly not obligated for that log property, but just be aware that you can do that. Now a cotangent's cool because it's in log form already, right? That's log form. Denominator is sine, derivative is cosine, that's up top. Don't have to do no magic bullets here, just straight up natural log absolute sine. No magic bullets here, just straightforward. And if you wanted to go through the 6-step extra process of substitution, you can. Let u be sine, and then du would be cosine dx, and then you'd have a du over u. You'd integrate that and get natural log absolute value of u, and then you would back substitute. Or you can do all of these. Log form is just a shorthand for substitution, u sub. And then secant, we just did secant a second ago. So the magic bullet here is multiplying up and down by secant plus tangent. And if you multiply by secant plus tangent, you get that it's in log form. We just went through the details on the last slide, so I won't write all the details, but you get that. And you'll take this secant here, and you're going to distribute it to there and distribute it to there, and then you'll have that the denominator's derivative is the top. Cosecant is very similar. Cosecant, once again, we sort of are basing our process here on the fact that we already know, because we've looked at integration tables, that the four trig functions other than sine and cosine integrate to log functions, so we should be able to put this in log form. Let's try something similar to what we did with secant. So we said the magic bullet, the multiplication by 1 for secant, we found by taking its derivative and then kind of separating. What's the derivative of cosecant?
Cosecant.
Minus cosecant cotangent. So if we do a similar type of thing, we could do minus cosecant minus cotangent. If we just leave the minus sign in there, this will work. So very similar to the sec plus tan. We can do minus 1 times cosec plus cotan. And then what I'm going to do, let me write the next step down. I'm going to factor out a minus from the denominator and put that minus out in front. And then I'm going to distribute in the numerator. So we're going to have minus cosecant squared and minus cosecant cotangent. So the minus that's in the denominator, that's the one I factored out to the front, and I left the one in the numerator, distributing that cosecant function across. And let's see, is it in log form? What's the derivative of cosecant?
Negative cosecant cotangent.
Negative cosecant cotangent. So the derivative of cosecant, all right, that's right there. And then what is the derivative of cotangent?
Negative cosecant.
Negative cosecant squared. It is now in logarithmic form. We know that if it's in log form, we could use u substitution and let u be the denominator, but we already know how this plays out. This is going to be minus natural log absolute value of the denominator plus c. So just as a reminder, try to get that embedded into your brains. All four trig functions other than sine and cosine integrate to logs. And if they integrate to logs, you should be able to put them in log form. So let's take a look at this. So I'm going to let you all try this. So the integral of secant squared, we just did it using that reduction formula in that big table of reduction formulas. But I want you to try it this way. So we have seen integration by parts with a twist. We've seen it if you have an e to the x and a sine multiplied together, or an e to the x and a cosine. And what I'm saying here is that let's try integration by parts with a twist by separating the secant cubed into secant times secant squared, and then applying the integration by parts formula. So you all try that. So let u be secant and dv be sec squared, and see if you can use integration by parts with a twist to get it. Ooh, I forgot my dx. Bad, 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 bad. Is the uv minus integral of v du, is that kind of embedded in your head by now? So ultraviolet voodoo, UV minus integral of voodoo, VDU. So remember, with the integration by parts with a twist, it's going to be really helpful to call the original integral something, some letter, I, omega, something, because you're going to end up with an algebraic equation. Let me know if you have a question or if you're getting hung up. Yeah.
So I can distribute this minus negative. So let's distribute this to minus and subtract.
Yeah, so something's wrong somewhere. Negative C minus the HEV minus negative U. Let's see what we do here. So U equals tangent. Tangent is secant squared. This is not an integration by parts here. This is just regular U substitution, right? Because if you let U be tangent, something's fishy right there. Let me see, what is it? Where are my glasses? I don't need them. You said tangent. But you can do it, so that should be fine now. So then. So I think what this is telling us is that this technique, I was going to do it a different way, so this is super interesting to see. My read on this technique is that it's just not working. Basically, if we do integration by parts a second time, we're undoing what we did the first time, and that omega minus omega sort of creates a conflict. So my recommendation here is that instead of trying to use integration by parts again, use a trig identity for that tan squared. Try that. So when we get to this second integral that is created, this one that has secant times tan squared, there's a couple of things. So one thing that Maxwell was doing that gets kind of hairy is that this actually, if you try to do integration by parts a second time here, you end up with omega minus omega, and that's not working. So when I first saw that, I thought, oh, maybe there's an error somewhere, but I didn't see any errors. So I'll double check that, but it looks like integration by parts a second time just doesn't work. That it's not going to, it undoes what we did in the first step. So what I'm seeing here first is that we just did a whole bunch of things when we have products of secants and tangents. And the rules when we had products of secants and tangents were if secant was to an even power, we did something. And if tangent was to an odd power, we did something. And let me just go back and show you that there was an alternative that said if neither of the special cases work, then use a Pythagorean identity. So let's come back here for a second. And so this is the case that we're in down here. So the power on secant is odd, not even, and the power on tangent was even, not odd. So if neither of those two cases work, convert the tangents, because the tangents now have an even power, And if the tangents have an even power, you can convert with the Pythagorean theorem. So that's going to be the strategy that will work in this case. So the strategy here, we have a product, it's not working. The power on secant's odd, not even. Power over here is even, not odd. So I'm just going to convert these tangents. So we know that tan squared is secant squared minus 1. So we have that. And let's go ahead and separate all this and see what we get. So inside here, we're going to have secant cubed. And I'm going to break this into two separate integrals. So then we're going to have a negative secant. And there's a negative out in front, so it's going to be plus integral of secant x dx. So we end up with that. And so here is the twist part. The twist part is that we have come up with what? What is that? If I call the original integral omega, what is that right there?
Omega.
That's omega right there. So we call the original integral omega, so that allows us to do this. So this is going to be minus omega. And we know already, we've done it a couple times today, that the integral of secant is the natural log of secant plus tangent, absolute value. And I'm going to put in a plus c right here because we just did that indefinite integral. So now we have omega on the left, we have a negative omega on the right. So if we add omega to both sides, that is going to give us the following. We have that. We already have that random plus c over there, so we don't need another one. And what is our final step to isolate omega?
Divided by 2.
Divide by 2 is our final step. So therefore, omega will be 1/2 sec tan plus 1/2 ln absolute sec plus tan plus constant of integration. So that'll be our final. Using integration by parts with a twist. So we'll see this a lot of times. Question?
How in the integral you have secant x tangent squared x? How do you get that, the secant x times secant squared of x?
This piece, how do we get to here?
Yeah.
So the secant is just dropping down, and we're replacing tangent squared with secant squared minus 1 from the Pythagorean theorem. So our Pythagorean theorem, if we draw the triangle, so the triangle that relates is this triangle, if we have an angle of x. So that makes sense? So having that triangle in your mind is how we're going to sort of memorize the Pythagorean theorem for secant and tangent. All right, let's see where we're at.
Hey, sorry.
Question, Kim?
For
Sure.
that one, it's exactly like how it's cosine plus, sine plus cosine equals 1. And so it's
Sine squared plus cosine
Yeah,
squared
yeah.
equals 1. Yep,
it's exactly like lined up like
exactly. So here we would say that the sum of the squares of the legs will be the square of the hypotenuse. So we'll have this. So that's kind of the primary Pythagorean relationship for secant and tangent. And then if we wanted to isolate tangent, we would subtract 1 from both sides. So depending on what you're replacing, so if we wanted to isolate tangent squared, we would have secant squared minus 1 over here. Yep.
On the third step, where we go from secant x, integral of secant x times secant squared x minus 1, how does it go from that to the integral of secant cubed x plus?
Gotcha. So when this distributes over to here, we're going to get minus integral secant cubed. And then when it distributes over to the 1, we're going to have minus secant of x in here. And if we distribute this minus sign, so that minus out in front is going to make a negative for the secant cubed, and it's going to turn this negative secant into a positive secant. You see it? Other questions on it? Yeah.
Where did the log form come from?
Going from here to here.
Yeah.
So that's what we did on the prior slide. So when we look at secant,
okay.
right, anytime we have a trig function other than sine or cosine, it's going to integrate to a log. So the log form that we use for secant is to multiply denominator and numerator by sec plus tan, and that's in log form now. So we did the sort of details of that on this page over here. So if we multiply by sec plus tan, we get sec squared plus sec tan, and the derivative of secant is this, the derivative of tangent is that, so now it's in log form, so the integral of secant will be that, natural log of secant plus tangent. Other ones from that example? So the hardest topic on this exam for most people is the topic of trigonometric substitution. So that's where we're going next. And trigonometric substitution is not hard if you stay up on it. It's one of those topics, though, that if you put it off, you're going to be in a quagmire. So trigonometric substitution, you want to just don't get behind on this because it is probably the hardest topic in this unit. So we have seen some integrals that we just don't know how to integrate. Like, for example, when we have something like this. That's a pretty simple integrand, but we don't know how to integrate it. If there happened to be an x on the outside, you could use substitution. But if there's not an x on the outside, substitution's not going to work. And so we have a lot of these situations where we end up with sums and squares, sums and differences of squares. And so this one inside here is a difference of squares. Inside here we have a sum of squares. And there's a lot of those that just don't work with regular U substitution or integration by parts or anything like that. And so what we need to do is come up with another technique to deal with sums and differences of squares. And that's what trigonometric substitution does. When we see sums and differences of squares and we can't do it with regular substitution or with integration by parts, then usually it's going to be trig sub. And so we are going to see three separate cases. And these cases, when you look at these basic sums and differences of squares, should sort of remind you of the Pythagorean identities. It looks very Pythagorean-like. So let's take a look at what I mean by that. So if we look at this Pythagorean identity, here we have a sum of squares. And a lot of times we could refer to this just so that we're talking about the left side here. We could say the sum of squares with 1, or in math parlance, a lot of times they'll say a sum of squares with unity or 1. So if we have a sum of squares with a 1, right, that's going to be equal to secant squared. Over here, if we rewrite the basic Pythagorean theorem like that, then we have a difference of squares with a 1. Down here, if we take this Pythagorean theorem and rewrite it this way, we've got a slightly different form of the first one. So I usually will say this is a sum of squares with a leading 1. This is a difference of squares with a leading 1. This is a difference of squares with a trailing 1. So the 1 in these differences is either going to be positive or negative. So here we have a leading 1, which is going to make it positive, and here we have a trailing 1, which is going to make it negative if we have a difference of squares. So the important thing to notice here is that we are taking a sum or a difference of squares and we're turning it into a single square. Like the biggest issue when you look at this right here is that you cannot break this apart, right? You can't distribute the square root. So that square root is sort of a roadblock for us right now. But if we could turn this sum of squares into a single square, then we could go somewhere. And so that's kind of our strategy, is that, hey, if we can take our sum or difference of squares and turn it into a single square, we can use that square root. We can then implement the square root. But as soon as there's two terms inside the square root, we're kind of stymied. So that's kind of where we're going. So when we have this sum of squares, we're seeing this sum of squares, the idea is that, hey, what if we let u be this tangent function? If we let u be tangent, then we would have 1 plus tangent squared. And then we could say, oh, 1 plus tangent squared, that's secant squared. And that's going to reduce that sum of squares into a single square. In this case here, if we have a difference of squares, we could say, oh, well, what if we let u be sine? If we let u be sine, then we're going to have 1 minus sine squared. Pythagorean identity will collapse that to cosine squared. And the third one, in our integrand, if we see a u squared minus 1, we can say to ourselves, well, if we replace that u with secant, then we're going to have secant squared minus 1, and that'll collapse to tangent squared. So that's the essence of integration with trigonometric substitution, is that we want to pick a trig function, and there's only 3 that we're picking. You could get clever if you wanted, but sine, secant, or tangent, those are the only 3 that we're going to use. You could use the others if you want to be a contrarian, but all you need is one of these 3, and it will work. So once again, it's going to be really helpful to have the 2 Pythagorean triangles really clear in your mind so you can be bumping back and forth. Tan squared is secant squared minus 1. Secant squared is tan squared plus 1. Having that in your mind so you can move around quickly is helpful. And of course, the basic one. So here, sine squared, cosine squared, sum of the squares equals 1. You can do 1 minus sine squared is cosine squared, or 1 minus cosine squared is sine squared, just being able to manipulate those triangles. Okay. Now we also are going to have to know our 3 basic integrals that lead to inverse trig functions. So here are the 3. The one that we use the most is that one. So we need to know all 3, but that one we use the most by far, and then that one the second most, and the inverse secant one we use the least by far. So these 2 are super important because they do show up in practice quite a bit, especially inverse tangents. So you want to have those 3 in your mind. Now, one way, we just sort of talked about the differences of squares. Let's just look at this for 1 second. So inverse sine is over here on the right, but this is connected to a 1 minus x squared, a difference of squares with a leading 1. And we just said that, oh, a difference of squares with a leading one, it's like you let u be sine, or you let, that u be replaced with sine, and that will all turn into cosine squared. Same, there's sort of that pattern here. 1 minus x squared is connected with a sine, 1 plus x squared is connected to a tangent, and x squared minus 1 is connected to a secant. So there's kind of that reinforcement to help you remember which integral turns into which inverse trig function. So let's try one of these, and then we'll get through one. Okay. Now, when you look at integration tables, they have the a squared minus x squared or a squared plus x squared. My preference, so that we only have to remember minimal, so if we can put things into this basic form where we have leading ones or a trailing one, then we just have to remember this, and we don't have to remember where there's going to be an a. So if you look back at those integration formulas, it's like 1 over a times inverse tangent and so of x over a. So there's a bunch of a's in there also. My strategy is to use a little bit of algebra so that we always are dealing with a leading one or a trailing one, and we don't have to think about whether we put a 1 over a in front or not a 1 over a in front. So just to reduce what we have to memorize, let's just memorize that. Then it's going to be a little easier. And this will also help to reinforce some algebra that's going to be useful in the long run. So I look inside the square root, I see a difference of squares. I want to turn it into a difference of squares with a leading one. That's going to make my life easier in the long run. So what I'm going to do is factor that 4 out. So if I factor this 4 out, first off, is it in the numerator or the denominator? Denominator. And when that 4 factors out of the square root, it's going to become a what? A 2. So we're going to end up with a 2 in the denominator. Now, when you're looking at it, you're saying, wait, there's no 4 with the x squared. So what do? Well, we use our magic bullet, right? There's no 4 here, but we could imagine multiplying by 4 over 4. So then when we factor out, this 4 and this 4 are factoring to the front to become that 2. So what are we left with then over here? We're left with x squared over 4. And what I want to do is write it as a square. So I'm going to write it like that. So now we've taken this difference of squares with a leading 4, and we've turned it into a difference of squares with a leading 1.
What if say the 4 was a 5, what if it wasn't a perfect
So
square?
if it's not a perfect square, any idea what this denominator would be? So let's take a look. So let's suppose we had 5 minus x squared. Okay, we say, yeah, we want to factor out the 5 for whatever reason. So we're first going to say, okay, well, let's just use our magic bullet and multiply by 1. So then that 5 factors out, and we have 1 minus x squared over 5. But if we want to write that as a single square, any ideas how we could write that as a single square? X over what quantity squared?
Root 5.
Root 5, exactly. So if it's not a perfect square, then we're going to be forced to leave a square root in there. Yep. So is everyone sort of following that logic? If we don't have a leading one and we want to force it to have a leading one, magic bullet is to multiply by 1 in the correct form. That 5 factors out, and now we have a difference of squares with a leading 1. So that's going to be our algebra that we're going to do in this section, and getting that algebra down is going to be very useful in the long run. So now we say to ourselves, we can't break apart this square root U substitution's not going to work because the derivative of this quadratic is a linear, but that's a quadratic, so that's not going to work. So we want to somehow be able to use that square root. So we need to combine what's inside the square root into a single square. So we're saying to ourselves, 1 minus what squared is going to be a single square? And we only have 3 choices, sine, secant, or tangent. 1 minus tangent squared is not an identity. 1 minus tan squared is not an identity. Tangent's got a t in it. It's always going to be with the plus. Tangent will always be with the plus. So if we know that it's only sine, secant, or tangent, and it's not tangent, it's sine or secant, 1 minus sine squared is cosine squared. 1 minus secant squared, it's going to be a negative number. Right? The identity is secant squared minus 1 is tangent squared. So the only choice that's going to work here is let's turn that part into sine of theta. So if we turn that into sine of theta, that means we want to turn all the x's into thetas. That's our goal. So we take the derivative of both sides. So on the left, we end up with 1/2 dx, and on the right, we end up with cosine of theta d theta. And that should be enough to convert everything. Let's see. So first off, the limits, let's deal with the limits, not right this second. Let's wait. So x squared. Oh, and I dropped my dx. We need a dx in there somewhere. So x squared, if we look right here, if we isolate x, we get x equals 2 sine theta, so x squared is 4 sine squared theta. 4 sine squared of theta. Okay, everyone okay on that one? So we're replacing the x squared. We look here, we multiply by 2, and then we square it, we get 4 sine squared. Now the dx. If we look at dx from the derivative equation, dx multiplied by 2, we're going to get 2 cosine of theta d theta. And then we go downstairs.
Where's the cosine coming from? Oh, yeah.
So if we isolate dx here, dx is going to be 2 cosine theta d theta. So that dx right up here is going to get replaced with 2 cosine of theta d theta. And then down in the denominator, we're going to be left with 1 minus sine squared of theta. So we're good there. Now, limits of integration. We can convert them for sure. We know how to convert. We could plug in the root 2. These are x limits. So we can plug in the x equals 0, the x equals root 2. In my experience, it's easier to just forget about the limits and then at the very end go back to the x limits. Instead of converting to theta limits, do the integration with respect to theta, but then do back substitution so you're back to x, and then use the x limits. So instead of actually finding the theta limits, let's just put some temporary limits up there that we don't even find, but they're not thetas, so they're not x, so we don't want to put these because they're not x's. So we were never even going to find them. Excuse me. Okay, so here we go. Looks to me like we have a constant of 4 coming out to the front, 8 divided by 2. And then inside in the numerator, we have sine squared of theta, cosine of theta in the top. And in the bottom, 1 minus sine squared is what?
That's cosine squared.
Cosine squared. And then square root of cosine squared is cosine if you're in quadrant 1 or quadrant 4.
Absolutely.
So technically it's absolute value of cosine. But if we look up here and we look at our x limits, So x limits are 0 to root 2. And then we look down here. So if we plugged in a 0, we'd have sine of 0. Sine of theta is 0. And up here we'd have sine of theta equals root 2 over 2. So that means we're in quadrant 1. So that means we can just take the square root of cosine squared and get cosine. And this book is, most calc books try not to really screw you up by doing a bunch of that domain shifting issue. So 90% of the time, you can just rest assured that the square root of cosine squared is cosine, the square root of sine squared is sine. There might be one question in the homework where they try to throw something sneaky in there. But generally, you can just do it. So then we're in that situation. Cosines, of course, cancel. So those cancel. And then we have to integrate sine squared. And we know to integrate sine squared, we have to, for sine squared or cosine squared, what do we do to the power?
You gotta reduce it.
Reduce it. So we've got to use those power reduction identities whenever we have a sine squared or cosine squared. So sine squared becomes 1/2. So I'll pull the 2 out in front in the denominator of what? Sine squared becomes 1 minus cosine of how many theta? 2 theta d theta. So the identity says 1 minus cosine 2 theta over 2. The over 2 factors to the front. So this will give us 2. And then we integrate and we get theta minus. The integral of cosine is sine of 2 theta, but then we have reverse chain rule, so we have to divide by 2. So we end up with that. And we have an identity we can use here. That sine of 2 theta, that's a very common identity. That's a double angle for sine. That's 2 sine of theta cosine of theta. So we're going to use that right here. So we're going to have 2. This is going to be 2 sine theta cosine theta. All that's divided by 2. All right, the 2's cancel. All right. Now we need to back substitute. We don't want to find the theta limits. That's kind of a hassle. Most of the time, it's easier to go back to x limits. So here is where we need to use our original let statement. Our original substitution is right here. So we have to use that. And what we are going to do to make this work is the following. We're going to draw a triangle. And the triangle that we are going to draw, you should always draw it as if it's a triangle in quadrant 1. And you're drawing this triangle that satisfies this picture, right up, or this equation right here. So theta is always down here in the left, like it's quadrant 1. And then we have that sine of theta is x halves. Well, we know that sine of theta is opposite over hypotenuse. So the opposite over hypotenuse has to be x over 2. Well, then we use the Pythagorean identity to figure out the missing side. That is going to be root 4 minus x squared. Sum of the squares of the legs is the hypotenuse squared. This triangle tells us everything we need to know to get rid of all the trig function, any trig function that appears inside there. Cosine is the square root over the hypotenuse, adjacent over hypotenuse. So any trig function that shows up over there, we can come to this triangle that we get from our substitution step, come here, and we can figure out the trig function. So we will have 2 theta. We come up here and solve for theta. That's inverse sine of x halves. Inverse sine of x over 2 minus sine of theta is x over 2. Cosine of theta is square root 4 minus x squared divided by the hypotenuse, which is 2. Now we're back to x limits, 0 and root 2. So now we're back.
Why is it divided by 2?
Because cosine is adjacent over hypotenuse. So we're replacing this cosine, that cosine right there is getting replaced with this, which comes from the triangle. Cosine is adjacent over hypotenuse. And sine is opposite over hypotenuse, x over 2, which you can see in 2 different places. And so, final answer. We've got to plug in our limits of integration here. So we have 2 multiplied by. First, we're going to plug in this root 2. So plugging in root 2 here, inverse sine of root 2 over 2. So inverse sine is the angle on the right with a sine value of root 2 over 2. So what angle on the right has a sine value of root 2 over 2? Pi over 4, exactly. So pi over 4 for that. Root 2 goes in here, and you square it, and you get 2. 4 minus 2 is root 2. And then you plug in a root 2 for this x, so you have root 2 times root 2, which is 2 in the numerator, 4 in the denominator, so that's 1/2. And then we subtract off this antiderivative evaluated at 0. What's inverse sine of 0? That's the angle on the right with the sine of 0. Angle on the right with the sine of 0 is 0. So right there, that's going to be 0. And then we minus a minus, which gives us a plus. We plug in 0 right here, and that gives us, plugging in 0 there,
It's gonna be 0.
we're going to get 0 because we're going to have a multiplicative factor of 0 there, so that'll be 0 also. So this 0 is not contributing anything down there. So our final answer is going to be whatever this is, so pi over 2 minus 1. So no individual step is super hard, but trig sub just has a lot of tendrils going all over the place. So can anyone formulate a question?
Yeah, so what did we just find?
So we just evaluated this definite integral of this function that had a difference of squares in it.
Okay.
So trig sub is when we have differences in sums of squares. It gives us a root in to find the definite integral. That's what we did. We found the area under that curve.
I'm telling you, this is why Newton died a virgin. It's
Yeah, he was busy. All right, let's stop. Let's take a break. Let's take a break. I feel like we. It's just as painful, or worse. Worse or better? Could be better. Could be better.
Just because it's a plus doesn't mean it's
Could be better. Positive. Think positive. It's got a positive.
I hate tangents.
Okay, so Now this one, we don't have that algebraic little nuance in the beginning. We already have a sum of squares with a leading 1. So we don't have to deal with factoring. So I know that arithmetic and algebra can sometimes be the downfall of your calculus problem. So here we're pretty psyched that it's already a 1. And so we know that it's going to be tangent. So this is just going to be a straight up thing like that. We're just going to replace x with tan. And our strategy, again, is that if we have 1 plus tan squared, we can collapse that to secant squared, and then we can deal with this root thing. Right? That exponent 3 halves has a square root quantity cubed. And so that substitution is going to allow us to then implement that exponent. That exponent can't be implemented when there's a sum down below or a difference. Right? We can't break it apart. So that's going to be our strategy. Let's see. So derivative of tangent is secant squared of theta d theta. So we've got that. Now we've got to turn all our x's into thetas. So we come up here. This also is a indefinite integral. So there's a little less brain power there. We don't have to think about unit circles and inverses quite the same way. Okay. So dx is secant squared of theta d theta. So that's going to go in the numerator. And then down below, we have 1 plus tan squared to the 3 halves. So 1 plus tangent squared of theta to the 3 halves power. So there is what we were looking for. All the x's have been turned to thetas. It's an indefinite integral, so we don't have to bother with any limits, so that's nice. And then we do the 1 plus tan squared, that's secant squared. So we're going to be dealing with, let's see, secant squared, 3 halves, d theta. All right. And then secant squared to the 3 halves is secant cubed, power to power, multiply the exponents. 2 times 3 halves is 3. So we have a secant squared up top. We end up with a secant cubed down below. So we're going to cancel out 2 of the secants. We're going to be left with a secant down below. And what does that simplify to? Cosine. Oh, man, there's a nice test question. That's not too bad. And we don't even need our triangle in this case. At this, not well, maybe we will. Yeah, we'll need it. Okay, not too bad. Now we just have to get back to x. So we do have to draw our magic triangle down here. So always draw it as if it's in quadrant 1. Put theta right there. Tangent of theta is x, so that means rise over run has to be x. Rise over run is x. And then we do the Pythagorean theorem to get to the hypotenuse, so that's going to be the square root of 1 plus x squared, or x squared plus 1, depending. A lot of people like to write it as 1 plus x squared. And so from our magic triangle, what is sine of theta?
X over the square root of 1 plus x squared.
So we're just doing opposite over hypotenuse from that triangle. And that is about as easy a trig sub as you can ever imagine. Not that tangents are always easy, but that one worked out pretty well. So that gives you a little bit more of the flow of the process. So we took away some of the extraneous stuff. Didn't have to deal with the arithmetic if that wasn't a 1. Didn't have to deal with the trigonometry if we had limits of integration. So that's the essence of trig sub.
Did you happen to skip over an example?
Did I?
I think you did.
Oh. Any questions on this one? We'll go back. There was a second one on that page.
I
That
think
page
so.
felt like it had enough.
You moved it down.
I got it out of the way. Oh, shucks. All right, well, we know it can't be quite as easy as this one. Let's see. Let's go, yes. Oh, way down there. All right, so let's go ahead and nail this one out then. Don't want to miss one. Good eye. So we see a difference of squares, and our goal is to just rewrite it with arithmetic so that we have a difference of squares with a leading 1. So what we're going to do is factor out the 36, and what's going to come out of this integral if we pull out a 36 through that root?
6.
6. So that's going to come out. We still have the integral. This now becomes 1 minus. And there was no 36 here, and so what we've kind of started to see is that when we use our magic bullet of multiplying by 1, the piece that's coming out to the front, this 36 and that 36, is becoming that 6. So we're left with t squared over 36, but we want to write that as a single square. So how would we write t squared over 36 as a single square?
T over 6.
T divided by 6, quantity squared. Good. Perfect. And so now we have that. And now we're in the situation where we have to decide, do we want to use sine, secant, or tangent for our substitution? And only one of those three will work, sine, secant, or tangent. It's not tangent because it's not a plus, so it's sine or secant. And when it's 1 minus, we use sine. Because 1 minus sine squared is an identity. That's cosine squared. Do you see that 1 minus secant squared is not an identity? What is that going to equal?
Negative number.
It's going to be a negative number. If we look at our triangle has tangent there, secant there, and 1 there. If we do 1 minus secant squared, this is going to be minus tangent squared. And that is not good because we can't take the square root of minus tangent squared. Right? All these things have roots and things, so that is not what we want to do. So it's got to be sine. So we are going to take the t divided by 6. We're going to make that sine of theta. And if you want, if it's easier for you to put the 6 over here before you take the derivative, totally fine. It's up to you. So then dt will be 6 cosine theta d theta. And our goal is to get rid of all the t's and turn them into the thetas. So we're going to have 6 integral square root 1 minus sine squared of t. Excuse me, sine squared of theta. And the dt becomes 6 cosine of theta d theta. So this will be 36 integral. All right, 1 minus sine squared of theta. Cosine squared of theta. We'll write this step in. And here technically we have to be careful. The square root of cosine squared is only cosine of theta if we're in quadrant 1 or 4. In this book and in most calc books, if you have this, we're just going to assume. Because as soon as you put absolute value of cosine, you're stuck. You can't do anything. You can't integrate it. You'd have to go into a piecewise defined, like, pain in the neck thing. So we always, in this book, unless otherwise indicated, we're going to assume that you can just take the square root and get the positive result. So I'll have that. Square root of cosine squared is cosine. Cosine times cosine is cosine squared. And then how do we integrate
Reduce the power.
reduced power? So 1 plus cosine of 2 theta divided by 2. We'll put the divided by 2 on the outside. So this will be 18, and then integrate. The integral of 1 is theta. The integral of cosine is sine. Reverse chain rule says we have to divide by 2. So we get to that position. Sine of 2 theta is an identity. Sine of 2 theta is 2 sine theta cosine theta. Double angle identity. The 2's will cancel. And then we convert back to x. Or t in this case. Whatever the letter is. Let's go purple triangles. So we draw our triangle as if we're in quadrant 1. Sine of theta is t over 6, so that looks like this. Sine is opposite over hypotenuse. We want that to be t over 6. That allows us to use the Pythagorean theorem to find that our missing side is 36 minus t squared under the square root. And the more you do of these, the more you start to see that your missing side should look a little bit like the original. There should be something common from the original. It might be off by a scalar multiple, but that missing side should match up with the original. All right, so let's see if we can complete this one. So we have 18 theta. When you look right here, if you isolate theta, theta is the inverse sine of the left-hand side. So that's going to be what we replace theta with down here. Inverse sine of t over 6. Plus sine of theta. That's t over 6, which you can get from your substitution step or from the triangle. T over 6 is sine. So we have t divided by 6 multiplied by cosine of theta. Cosine of theta, we look at the triangle. Cosine is adjacent over hypotenuse. So we'll have the square root of 36 minus t squared, all divided by 6. Last step, simplify this a little bit. 18 inverse sine of t divided by 6 plus, let's see, so we have 18 over 36, which is a half. So 1/2 t square root, 36 minus t squared, plus c. All right, questions on that? The pain is lessening. I can feel it. The pain is lessening. There's still some pain. All right, let's take a look at a tangent one that's got limits of integration. So limits of integration, z is between 6 and 6 root 3. So, first thing, we unfortunately see that, oh gosh, We don't have a sum of squares with a leading or trailing 1. We have a sum of squares with a 36. So what we're going to do is factor that 36 out. It's going to come into the denominator, right? And what number should be sitting in front?
6.
It would be 6 if the exponent were a half. Right? Whatever the exponent is going to come along. So the ones in the past, we had a square root, and we were pulling it through a root, and it became a 6. But now the power is not 1/2, the power is 2, so it's going to be a 36 squared. Yeah, so whatever that power is, that comes along with it. So in this case, it's a power of 2. Well, hopefully something will cancel, and we don't have to actually figure out what that is. We'll see. So then in the numerator, we have z squared. And in the denominator, what plus 1 squared?
36 squared.
What's going to go right here? If we want to write this as a single square, what's going to go there? Z over 6. Because remember that this doesn't have a 36, so we multiply it by 36 over 36. The 36 here and here are factoring to the front to that. So what we're left with right here is z squared over 36. So the z squared over 36, if we want to write it as a single square, is z divided by 6, quantity squared. So z over 6, quantity squared. Any question with that? Do we need to go through that again? Does that make sense? Good. Okay. Everyone is totally on track. We'll put z over 6. So with our substitution, sine, secant, or tangent. Tangent because it's a plus. So that z over 6 will be equal to tan of theta. We take the derivative of both sides, or if you want to get rid of the fraction before you take the derivative, if that's easier, whatever works for you. Then we take the derivative of both sides. Derivative of tangent is secant squared of theta. So that is our substitution setup. We're going to come over and turn all the z's into thetas. And we're hoping that the 36 cancels at some point, so we can just leave it as 36 squared. We are going to use placeholder limits. Just going to let them be asterisks for now, not convert them over to theta. So z squared, we look right here, z squared is going to be 36 tan squared. Then the dz is going to be 6 secant squared. And then down in the denominator, we end up with tan squared of theta plus 1 quantity squared. So stare at that for a moment and make sure you see where all the parts came from. You start to see really clearly why some of you who are super sloppy and leave that thing off, it really matters, because that thing gets replaced with a different differential. Super important not to leave that differential off. All right, oh good, one of the 36's cancels. So we have a 36 right there that's going to cancel with one of the 36's in the denominator. And then we have a 6 over 36, which will reduce that to 1 over 6. And then we have our integration with some placeholder symbols. And let's see, numerator, tan squared theta secant of theta. Denominator, tan squared plus 1, secant squared, and then to the 2 is secant to the 4th.
Shouldn't the numerator secant be squared as well?
Oh, yes, it should. Thank you. Yes. Thank you. Tan squared, secant squared up top. Down below, tan squared plus 1 is secant squared, and then we square that. So, okay, I agree with this. This looks good. Or at least it looks correct. Maybe it doesn't look good. So the only simplification here is that secant to the 4th over secant squared, or vice versa, secant squared over secant to the 4th is going to reduce. So we have a tan squared over a secant squared. Okay. So here we've got a pile of tangents and secants. And our rule was if secant had an even power or tangent had an odd power, neither of those are applying here. Yes, the power in secant's even, but it's in the denominator, so that doesn't count. So we can't use one of those two rules. So the other piece of that said, if you have that situation where neither of the primary rules work, you can convert your tans, which are even, you can convert those to secant with the Pythagorean theorem. So that's where we're going to go, or one way we could go. Another alternative, if you have a pile of secants and tangents and the two primary rules don't work, you can also just convert everything to sines and cosines and hope for the best. That sometimes is going to work too. So we could make this secant squared minus 1 and go from there, or we could change the sines and cosines. Now what I'm seeing in my mind is that the secant squares, if we convert those to cosines, that puts a cosine squared up top. Tan squared puts a cosine squared down below, so there's going to be some quick cancellation there if we go to sines and cosines. So let's go that way. The other way is going to work out the exact same. You're going to end up with a... But let's just, because we're seeing this, we're going to take the tan squared and write it as sine squared over cosine squared. And then converting this becomes 1 over cosine squared, which when you flip it becomes cosine squared over 1. And when we do that, we see that, okay, these cosine squares are going to cancel. And that puts us into the integral of sine squared land, which we're getting very familiar with integrating these squares. How do we integrate sine squared?
Reduction.
Reduce the power. So that's going to be 1/12 integral with placeholder limits. 1 minus cosine of double theta. So sine has the negative, cosine has the positive when you're doing that power reduction. Remember, there's a division by 2, which is why the 6 became a 12. The division by 2 can be factored to the front. So we are now integrating. The integral of 1 with respect to theta is theta. Integral of cosine is sine of the same angle divided by the derivative of the angle. Placeholder limits. What do we do with the sine of 2 theta?
2 sine cosine theta.
2 sine cosine, exactly. Double angle identity. And the 2's cancel. All right. So now we have all of these thetas in our antiderivative. We need to go back to our original independent variable, which is z. So we draw our magic triangle as if it's living in quadrant 1. Put theta right down there as if it's a positive angle in quadrant 1. Tangent is z over 6. Tangent is rise over run. Opposite over adjacent. We can then find the hypotenuse. Hypotenuse will be the square root of 36 plus z squared. Beauty. I did restart this, didn't I? Okay, I did. All right, so now we just substitute. Does anyone have questions on the theta part? Are you seeing that the theta part? We just come up here and move the trig function to the other side of the equation with an inverse. That part okay? So solve for theta up here. Tangent moves through the equal sign to the other side as its inverse function. And then we have a sine theta and a cosine theta. All right, so minus. Sine theta, we look at our triangle. Sine is opposite over hypotenuse, so I'm seeing z divided by the square root of 36 plus z squared. So that's sine of theta. So sine of theta is this one. Cosine of theta is adjacent over hypotenuse, so I'm seeing this. So that one is cosine theta. Now our limits are back to z limits, so 6 and 6 square roots of 3. Before we evaluate, is there any part of this anti-differentiation substitution stuff that you aren't sure about? So I see an inverse tangent of root 3. I see an inverse tangent of 1. Let's go to the unit circle for a minute. Inverse tangent, let's make sure we recall a couple of things I want to point out. So if we are looking at the unit circle, obviously we have this angle of pi over 4. Inverse tangent of 1 is the angle on the right with a tangent value of 1, and that's pi over 4. Tangent of pi over 4 is 1. So that one we kind of know. Let's look at these two for a minute. So these two at pi over 6 and pi over 3. Let's just put the coordinates here for a moment. So that's going to be x is the longer leg for that one. X is the shorter leg for that one. So we have that. With tangent, tangent and slope are the same. So for this angle right here, pi over 6, tangent of pi over 6 is rise over run, y over x, blah, 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 however you want to think of it. And you get, if you rationalize the denominator, you get root 3 over 3. Tangent of pi over 3, again, rise over run, y over x, you get root 3. So, at pi over 3, the slope, the tangent, is root 3. And at pi over 6, it's 1/3 of root 3. It's less steep. So on the unit circle, when you're dealing with tangent values or inverse tangents, keep that in mind, that the steeper one is root 3 and the less steep one is root 3 divided by 3. It's 1/3 as steep. So let's see if that can help us here. So we end up with a 12th multiplied by right here. So if we plug in 6 root 3, we're finding the inverse tangent of root 3. So that's the angle in quadrant 1 with a slope of root 3. Right there. Angle in quadrant 1 with a slope of root 3. So that's pi over 3. And then we plug it in here. It's going to look a little messy here. So we're going to get 6 root 3 times 6. So let's not simplify it quite yet. Let's just try to make sure everyone sees where everything is coming from. So there's our numerator. Down here, when we square 6 root 3, we get 36 times 3. Okay, so 36 times 3. Let's come off to the side. So inside this square root, we have 36 plus 36 times 3. We okay with that? Because if you square that, you square the 36, you square the root, and you get what's inside the root. There's a few ways you can do this. This is going to turn into, isn't this going to turn into 36 times 4? And then it's a product, so you can split a root over a product. So that's going to end up being 6 times 2, which is 12. Okay. So that's all going to be 12 down in the denominator. And that's going to happen twice. Well, not yet. Okay, so we plugged in the 6 root 3 there, plugged in the 6 root 3 in the bottom. So let's see. So that's going to be 12. This will be 12 right there too also though, right? There's going to be 2 of those. I combined the numerators already, so I was just looking at one of the denominators. So it's going to be 12 times 12. And then we need to subtract off the evaluation of the antiderivative at the lower limit. And so that evaluation, let's just move this over there somewhere. Plugging in a 6, arctan of 1, angle on the right with a tangent of 1, pi over 4. And then minus a minus is plus. Now we're plugging in just 6 here. So 6 times 6 in the numerator is 36. In the denominator, we're going to get 36 plus 36. So that's going to be the square root of 72. And we're going to have the square root of 72 twice. So square root of 72 twice will give us that. So we should get a bunch of simplification here. So pi divided by 3 minus. Okay, 12 goes into 36 3 times. And then 3 goes into 12 4 times. So it looks like a square root of 3 over 4 minus pi over 4 plus root 72 times root 72 is 72. 36 over 72 is a half. We get that. The common denominator for all of this is going to be what? 12. So we can turn this into a single fraction with a 12 in the bottom. This has to be multiplied by 4. This has to be multiplied by 3. This has to be multiplied by 3. This has to be multiplied by 6. And that should give us our simplified answer, which is pi. And then the constants can only be rewritten. They can't be combined. Denominator, 144. So there is our what?
Area.
There's our area.
Gross.
There's the area underneath that hideous curve. Yeah, so Calc 2, lots of trig. I'll try to give you little refreshers to hopefully make it a little bit, reminders. Any questions on the inverse trig function values? Is that all coming back? All right. So let's take a look at, let's see. Was there any other on that page, or was that the end of the page? That was the end of the page? Okay, good. All right, so the one we have not done yet is secant. So secant is a difference of squares with a trailing one. Difference of squares with a trailing one. Now, the first thing here is that, do you see that our integral has this form, that we want it to be a difference of squares, and the way that it's presented is not really as a difference of squares. They haven't created a single square with that first term. So we want to make that a difference of squares, so we want that first term to be, a single square, not 4 times a square. So that's our first step. And now we're ready. We're happy that we've got this trailing 1. We don't have to do any of that arithmetic mumbo jumbo. It's already 1. That's cool. So we are going to do 2x. That's going to be our substitution. We see that difference of squares. We would like to combine those 2 squares into 1, and we do that with trig. Sine, secant, or tangent. Obviously, it's not tangent because it's not a plus. It's not sine. Sine squared minus 1 will be negative. We don't want that. So there's only one function that's going to work, and that's secant. We're going to make that secant of theta. Take the derivative, and we'll get 2 dx equals secant theta tangent theta times d theta. So we have that. And now we're ready. We're ready for something. Theoretically. Ready for substitution, hopefully. So this will be, bless you, the square root of, let's see, 2x is secant, so we're going to get secant squared minus 1. And then the dx, we can put that in the numerator. We can extend this numerator. And that dx down here is going to be 1/2 secant times tangent. So the 1/2 I'll put in front, and then it's secant times tangent. So there's dx. Secant, tangent, divided by 2. Put the divided by 2 out in front. And then down below, we have an x squared. So we have to look over here and figure out how to get x squared. So if we isolate the x here, we have that x is equal to secant of theta divided by 2. So x squared is going to be secant squared over 4. So secant squared of theta divided by 4. We'll pull that out to the front in 1 second. So look at that for a second and make sure you see where all the parts came from. This will give us a 2 out in front. So that 4 is popping into the numerator, coming out in the numerator, so we'll have 4 divided by 2, which will be 2. Secant squared minus 1
Tangent squared.
That's tangent squared. Square root of tangent squared is tangent. This numerator is going to become, let's combine two steps. Scary. All right, so in the numerator, that becomes tangent squared. Square root of tangent squared is tangent. Tangent times tangent is tangent squared. We got rid of the 4 in the denominator, so now we have a secant that we can wipe out. So when all is said and done, we end up with tangent squared over secant. We find ourselves once again in that situation where tangent is not to an odd and secant is not to an even, so we can't do our the regular two primary rules for powers of tangents and secants. So again, we have two choices. Tangent is to an even power, so we can just convert it to secants using Pythagorean identity. We could do that. Or we could go to sines and cosines. Does not really matter here. Both of those techniques will work. Last time we went to sines and cosines. This time, let's not. Let's convert tan squared with the Pythagorean. So if we convert tan squared with the Pythagorean, tangent squared, if we think about that triangle, is going to be secant squared minus 1. Divided by secant. So we've got that. And then we split the fraction. We want that fraction to be split into two parts. So we're going to have 2 integral. Secant goes into secant squared secant times. And 1 over secant is cosine. So now we have that. So there's our integral of secant that we've seen a bunch of times today. Hopefully, we have done secant enough today that you are going to be familiar with its antiderivative, natural log absolute value of secant plus tangent. We're going to see that one so much, it's going to be second nature. That will impress your parents.
We gave up on that a long time ago.
That's good. So there is our antiderivative, our family of antiderivatives. Now we have to use our magic triangle to get back to letter x. So secant of theta is 2x. So we build this triangle as if it's in quadrant 1, and we need to satisfy this substitution. Secant is 2x. Secant is hypotenuse over adjacent. So we want hypotenuse over adjacent to be 2x. So the simplest way is that. Hypotenuse over adjacent to be 2x. That's the simplest way. That allows us to find our missing side over here. That is going to be 4x squared minus 1 inside the square root. Now we should be able to replace all these trig functions with some functions of x. All right, so we have natural log, absolute value, secant of x, so that, or secant of theta, that's an easy one, that's 2x. So secant of theta, hypotenuse over adjacent, 2x. Tangent, okay, tangent is opposite over adjacent, so that's going to be this, square root of 4x squared minus 1, minus sine of theta, opposite over hypotenuse. So minus square root 4x squared minus 1 divided by 2x. All that's plus c. So simplification here, there's not a lot we can do. We're just going to distribute this 2. And when all is said and done, that will be our final answer. All right, questions on that one?
Can you explain the triangle, why 2x is the hypotenuse?
Yes. Excuse me. So when we look right here at our triangle is always going to be built from looking at this. So whatever we're using for our substitution, that's how we build our triangle. We always think of this triangle as if it's in quadrant 1. You know, we're kind of thinking about this coordinate system here, if you will, like that. So we're always just sort of imagining it as a standard angle in quadrant 1. Secant is the hypotenuse divided by the adjacent side. And there are lots of ways to create hypotenuse over adjacent that's equal to 2x. We don't have to do it this way. This one is the simplest way. So we just want this dimension, the hypotenuse, divided by this to be 2x. So the simplest way to do that is just to let that adjacent be a 1. And then 2x divided by 1 is 2x. And then we're going to use the Pythagorean theorem, the hypotenuse squared minus this leg squared, to get the missing leg squared. Other questions? Good. All right, well, we only have a minute left. Is it possible to finish a trig sub in 1 minute? No. Not possible. I'll give you that minute. You can make it up. I'll give it to you back on the exam. Let you stay an extra minute. On the exam. That seems like a fair trade.
I'll take that.
Fair trade. All right, well, have a great weekend. Do a bunch of integration. Do a bunch of integration.
I think this is
Integrate until you can't
the
think
last
anymore.
thing we did.
Yeah.
Like chapter 6. Oh, no.
Oh, hey, honey,
The last-
that's a good question. I don't know if you noticed this handout that I uploaded and I forgot to tell you about. The engineering club right there. I don't know a ton about it, but I do know that it meets every Thursday at noon in 1406, which is right around the corner. So if you're curious about it, just go there at noon today and do engineering things. Show them how to integrate secant of x.
It's really cool. You should be there.
Are you part of it? Yeah. Yeah, so go. Yeah, that's a good idea. Thank you for reminding me.
Of course, I saw it.
I put it up there and then I forgot to mention it on the
Yeah, I thought you went over it. I thought you went over it.
No, I spaced it out. I spaced it out. I was thinking I was going to mention
That
it.
makes you do math.
So thank you so much for the reminder. All right, have a wonderful weekend. See you all Tuesday.